If you look closely at the history of science, it's really the history of humans continuously upgrading our tools for reliability. It started with simple observation, gathering empirical data by watching the night sky or measuring the tides. Over time, we realized our eyes deceive us, so we isolated variables through controlled experimentation. When that wasn't enough, we introduced statistical inference to filter out the noise, and eventually peer review to subject our findings to communal scrutiny. This continuous upgrading gave us a highly effective model for scientific progress. The philosopher Karl Popper outlined it clearly. Science moves forward by proposing bold hypotheses and then rigorously attempting to falsify them. This classical method of conjecture and refutation worked incredibly well for centuries, for one specific reason. The data sets were small enough and the math simple enough that human brains could intuitively check the work. Today, artificial intelligence acts as an active partner in discovery, autonomously generating millions of candidate explanations for everything from novel materials to complex diseases. But this massive output creates a critical bottleneck. We are facing a severe problem of opacity. When an algorithm predicts a vast three-dimensional protein structure, the mathematical steps are so dense that no human can intuitively verify the logic. This leads straight to the risk of automation bias, the very real temptation to accept machine outputs as truth, simply because we cannot comprehend the calculations behind them. If our brains can no longer act as the ultimate verifiers of these discoveries, Popper's classical method of refutation breaks down. The way we establish justified belief has to evolve. To solve this crisis, we have to transition into computational theory, relying specifically on a mathematical concept known as the asymmetry of knowing. This diagram of a massive labyrinth helps illustrate the P versus NP problem in computer science. Finding the solution to a maze this complex is incredibly difficult and time-consuming, but verifying a solution, checking that a proposed path successfully leads from start to finish without crossing a wall, is fast and straightforward. Because of this asymmetry, knowing something is true today doesn't mean manually recalculating the entire problem. It means designing rigorous boundaries and ensuring that no incorrect or flawed solution could possibly bypass our tests. Structural verification, rather than manual human observation, has become the core mechanism of scientific reliability. Since we can't manually check the AI's work, we have to build secondary algorithms whose entirely dedicated purpose is to interrogate the original AI. This interactive proof system operates like a high-speed interrogation between two programs, a prover making a claim and a skeptical verifier demanding evidence. The verifier sends continuous challenges, analyzing responses over millions of cycles until the dialogue corners the prover, exposing any hidden inconsistencies. Truth in the modern scientific era relies heavily on this mathematically enforceable credibility rather than slow human consensus. But what happens when the proof generated by the AI is so massive that even a supercomputer couldn't read the whole thing in our lifetime? This is where the PCP theorem comes in. The PCP theorem shows that if you format a complex proof correctly, any single error will systematically infect the rest of the data. Because the errors are encoded to propagate structurally, an algorithm can validate a massive dataset with near certainty just by checking a few small random portions. This image shows a physical microchip. When engineers design complex processors or cryptographic protocols, they use a process called formal verification. They translate the physical behaviors of the system into strict, verifiable mathematical constraints. We achieve absolute reliability not by looking at every single detail manually, but because the intelligent structure of the testing system makes hiding an error mathematically impossible. The hybrid epistemic system creates a working partnership where human judgment and machine generation collaborate to process information. This pyramid framework starts with AI generation producing explanations. That output moves to algorithmic validation, applying mathematical checks, then experimental replication for physical testing. The top layers are ours: documentation for independent scrutiny and human interpretation to extract meaning. Computation serves as the scientific method's most rigorous filter, extending our ability to process realities that exceed natural cognitive limits. And we will need that filter for the immediate horizon. As quantum systems offer massive new problem-solving capabilities, we face a daunting challenge: figuring out how weak classical algorithms can successfully verify the outputs of vastly more powerful quantum computers. As our raw computational power scales up, our methods of verification have to fiercely co-evolve right alongside it. Without that balance, we slip right back into total opacity. AI can explore an endless space of hypotheses, and complex algorithms can verify the underlying logic. But these machines cannot decide which questions are actually worth asking in the first place. Governing the risks, ensuring ethical access to these powerful tools, and interpreting what the data means for society remain irreducibly human tasks. The architecture of knowing will always rely on our judgment.